So we briefly mentioned malaria in this context, which obviously is mosquito-borne disease, and typically people spray DDT to kill mosquito larvae and so on. Remember, DDT became very unpopular in the 60s onwards when it became clear that it was carcinogenic. It was a carcinogenic, and it was causing problems for many birds like the pelicans and cormorants, and of course for humans as well. But and it got banned in many places. But over time, people have talked about bringing it back, and I think in parts of Africa and India it's still being used. So the cycle of environmental variables to water conditions to mosquito breeding, and then to humans and human behavior is not completely represented in the models, but you can kind of find the empirical relations between temperature, rainfall, and let's say malaria outcome, and see if a effective early warning system can be built. Similar things are done for dengue and meningitis and other vector-borne diseases, and of course also harmful algal blooms and pathogens, and things like cholera, and for Vibrio cholerae, Vibrio parahemolyticus, Vibrio vulnificus, and so on and so forth. Okay, so as long as you can find some empirical relation with habitat parameters like salinity, temperature, oxygen, chlorophyll, you can develop models and treat it as a engineering problem, where the goal is to keep improving the system. Okay, so this is one example of a dengue system where you are taking historical and live Earth observations data from satellites and other sources, feeding it to a dengue fever model that has been developed using available data, and it's also being helped by running a Vic hydrological model. I think this is variable infiltration capacity model, if I'm not mistaken, which tells you about the soil moisture and the soil water conditions which are relatable to mosquitoes, and water availability indices are generated from that, which feed into the dengue fever. It also takes forecasts of meteorological data, so that's where the S2S timescales come in. And there are also probabilistic forecasts of water availability coming out of hydrological models used for water resource management, for example. And then probabilistic forecasts of dengue incidents are made. So many times, as I said, these are no regret decisions. If there is a forecast made that dengue incidents are going to go up, then people can protect themselves from mosquitoes, sprays, shirts, nets, whatever, and staying out. Children have to be protected from playing outside, etc., etc. But they can be also made much more specific, so using geospatial data and other kinds of vulnerability data and so on and so forth. Here, probabilistic dengue forecast and observed dengue incidence rate categories for Brazil for June 2014 are plotted. A is the probabilistic dengue forecast for Brazil in June 2014. Continuous color palette ternary phase diagram conveys the probabilities assigned to low, medium, and high risk dengue categories. So you can see low, medium, high categories here, and it indicates where you are in the phase diagram. So you can see the details in terms of spatial information here, which is critical for local decisions. The idea is to take it as close to local, to the neighborhood scale as possible, because vulnerabilities can be very local depending on per capita income, education of the woman who's managing the household, and so on and so forth. And this is the observed category. So often the validations are run against reanalysis data and a mix of past health data and so on. Okay, so here we are looking Okay, low, medium, high. Category boundaries defined as 100 cases per 100,000 inhabitants and 300 cases per 100,000 inhabitants. The greater the color saturation, the more certain is the forecast of a particular outcome. So where they are darker, the skill is higher. Strong red shows high probability of high dengue risk. Strong blue indicates high probability of low dengue risk. Colors close to white indicate a forecast similar to the benchmark, so it's a kind of a even climatological probability. People are aware of how prevalent dengue is, and they can use this information in the context of what they already know. In B, we are showing observed dengue incidence rate categories for June 2014. Okay, so you can see that some forecasts were correct. Okay, so these are dengue incidence rates. Okay, so you can see how spatially explicit it can get. Here one can imagine that you can make it much more detailed when you work with various agencies. So you are looking at dengue control programs with public health field workers, data from sources, government, non-government. People also crowdsource the data these days, and this is what it is meant. This data from public, which is fed into the early warning and adaptive risk system, and recommendations for resource optimizations are used for prevention, control, and awareness and education. So the model is implemented to look at the outcomes and model evaluation, and is fed back to how to fine-tune it for the following season. So these are getting better and better, as we saw before. The more information you produce and more people find it useful, the more they will demand for better information, more local information, more time resolved information, and so on. In the COVID cases, you probably already heard of the so-called SIR and SEIR models, which are epidemiology models where there are various parameters and mathematical equations which track people in these boxes categorized as susceptible population, exposed population, infected and removed by death or recovered. And there is a parameter called R, which is the reproduction rate, if you will. It's the number of people infected by one individual. So if R is less than 1, the disease is not spreading very fast. But when R begins to get higher, 2, 3, 4, and so on, then the disease will spread very fast. Many centers, many universities, many academic departments started to run SEIR and SIR models for COVID, and they have examples from the Ebola and SARS bird flu experiences, which have helped. The SEIR models have helped in terms of planning for hospital beds, expected number of cases, preparing for another wave coming, and so on and so forth. Meningitis is a bacterial disease that affects the thin layer in the brain and I think in the respiratory system, if I'm not mistaken. You can read up. And there is a hot spot meningitis belt here, which is related to certain environmental conditions. It needs certain dryness, dust, and winds to carry it, and you can see this is a semi-arid region which is favorable for meningitis, and people have used that to make meningitis forecasts, looking at dust loading here from NASA, for example, and they are related to meningitis forecasts. So here we are looking at a European Center reanalysis ERA interim, 10-meter wind legend here. Humidity anomalies for November averaged over meningitis epidemic years of 1984, 96, 97, and so on. So you can see that there is no direct correlation with El Nino or La Nina. This was a La Nina, El Nino, normal, I think El Nino, and so on. So it depends on a combination of rainfall affected by external forces like El Nino and local seasonality and local winds, local land use patterns, dust, airborne dust, and so on. And shaded areas here mark statistical significance here in terms of meningitis epidemics during those years. So you can see that there is a skill in using these environmental parameters to predict for meningitis. Obviously, as we said, the idea is to just generate reliable information so that at least the no regret decisions of protecting against these diseases can be made and morbidities and mortalities can be reduced, so that system can be continuously improved and made more local and regional as well. Okay, it's a very good applications in terms of S2S. Let's come back and look at heat waves and then close out the chapter with some looking at issues for implementation.